Welcome, Pablo. Thank you for being here and taking the time to answer a few questions. I would like to start this interview with a more personal question. Did you always know you wanted to become a scientist, or was there a specific moment, book, or teacher that inspired you to follow this path?
For as long as I remember, since I was a kid, I like a lot to experiment and I like science. So I kind of always wanted to be a scientist, yeah. But having said that, I didn't always want to be the same type of scientist. So when I was in high school, initially I wanted to be a biologist, because I like biology. But then I started to like more and more chemistry and physics. And then ultimately, in my last year of high school, a teacher, my physics teacher, he mentioned to me that perhaps I could participate in this thing called the Physics Olympiads, which is a competition in physics. And I participated and I did well. And then I went to the Polytechnic University in Valencia. I had 2 free afternoons during my high school. So those 2 free afternoons I spent, at the Polytechnic University taking advanced physics classes. And then I got to learn more and more and more physics. And then I liked it a lot. So eventually it became clear that I should probably do physics, since I seem to like it a lot.
That's a trajectory indeed. But physics is very broad. What drew you exactly to condensed matter physics and quantum materials?
Initially, I wanted to be a particle physicist, in fact, a theorist. So at the University of Valencia, and especially 25 years ago or so, the most prestigious group, the group that had international visitors and postdocs and so on, was the high energy theory group. We all went to high energy theory. It was like almost by default, So I thought I was going to be a particle physicist. And I started my PhD actually, I specialized in high energy theory during my undergrad. Back then it was 5 years, the undergrad degree in physics in Spain. And then I went to do my PhD and I started as a particle physicist. It is very different to learn about something than to do research in something. And when I was at the University of California, San Diego, where I was doing my PhD. Initially, I was going to do my PhD there, and I realized that when I was attending the seminars, I was finding the most interesting seminars were the condensed matter physics seminars, where I was not so interested in the particle physics seminars. So then slowly I began to think that maybe I actually should do condensed matter physics, not particle physics. And then once I decided to make the jump, which took me 2 years. So it was actually a long process. I thought, well, if I'm going to make the jump, why not make the full jump and become experimentalist? Because I think that in high energy physics, theory is usually 10, 20, 30 years ahead of experiment, right? In condensed matter physics, I think experiment is a little bit of theory, ahead of theory, because the systems are very complex and often it's not easy to predict theoretically what's going to happen. So I thought, I like to be a little bit ahead, so let's do experiments. So then that's how I switched from particle physics theory to condensed matter experiment. That process took me 2 years, and it involved also changing universities. It was not a straight path.
Yeah, that's also very interesting because it shows the versatility of physics. I mean, you have the basic, let's say, foundation, but you can move from whatever topic you like. And also, I feel especially attracted to the quantum world. I am also an experimentalist, but many people feel a bit intimidated by the word quantum. To a regular person probably hearing us today, how would you easily explain what the quantum world is, or the quantum physics?
So it's true that quantum physics is very counterintuitive. It's important that people realize that quantum physics is just the theory that we have nowadays that explains everything, that explains everything, how nature works, starting with atoms and molecules, but ultimately how everything works. Quantum physics explains this chair, explains your iPhone, explains your computer, explains the walls of your house. Quantum physics explains everything, but it is most relevant in appreciating the key aspects of quantum physics, which are important, these become more relevant or more apparent when you look at small things. Yeah? And then one has to be able to explain to people, matter is made of, something called atoms, and atoms have electrons, protons, and neutrons. And when you look at very small things, such as atoms or as electrons, the properties, it's not that they change, they've always been like that, but they differ from the way tennis balls fly around. So when objects are very small, or when they move very fast, they have different properties, or apparent, their behavior is different from the one of macroscopic objects that we're familiar with. And then quantum physics is particularly useful when we have to explain those behaviors of very small, tiny objects.
Do you find something specifically exciting about studying electrons in materials, or which is like the most fascinating thing about electrons in a material? Electrons,
at the very big picture level, right? Electrons are responsible ultimately for the chemistry, and therefore, it's not that they're more important than protons. The protons have to be there,
Yeah.
Otherwise it would be a disaster, if we were not charge neutral. But electrons are the carriers of electricity. In my group, we do quantum electronic transport. So what we measure are mostly the electrons flowing. Okay, and the thing that I find fascinating, and this is something that it took me a bit longer to appreciate throughout my career, I started to realize what is the beauty of many electrons interacting with each other. And that is something which is very, it happens in all areas of physics, but it's most prominent, or is very prominent in condensed matter physics. The fact that it's very different, the behavior of a single particle from the behavior of many particles interacting with each other. And in particular, the behavior of a single particle is quite simple. We have an equation in quantum mechanics, which is called the Schrödinger equation. And in that equation, if you look at the behavior of a single electron, which can be in a bath of nuclei, etc., or in a crystal, in a solid with the potential of the nuclei, it is very simple. You can calculate very accurately the properties of this electron. That's how you calculate the bands of solids, etc. But we do not know how to calculate the properties of a whole bunch of electrons. 3, 4, 5, 10 electrons is very hard. And of course, it's impossible to calculate very precisely the properties of a system of millions of electrons, which are all interacting with each other through the Coulomb interaction. So the fact that theoretically we cannot calculate analytically those properties, we cannot calculate it numerically calculate those properties numerically with computers. We don't have computers powerful enough to do that. That means that there is a lot of room for experimentalists to discover things, because mostly you have to do the experiment and see what happens. And the most fascinating states of matter in the universe, and also in condensed matter physics, are states where many particles interact with each other strongly and they're involved. So that's something, the behavior of a system of many electrons is extremely rich, and it's responsible for behaviors which are extremely unusual, from superconductivity to the fractional quantum Hall effect, to many things. And that's something that intellectually is very appealing. Experimentally, the manifestations are dramatic, so it's also very appealing, to work in this area. And it's something that I really enjoy.
The quantum world sure is very interesting, but this also holds a bit of complication for an experimentalist, I believe, to be able to deal with electrons, a whole bunch of electrons at the same time. But this also gives new physics, I believe, because these interactions that you cannot predict, let's say, or it's very hard to give a precise number to characterize this, is where new phenomena appear. You discovered, or experimentally you proved this graphene bilayer magic angle. To a student hearing this from the first time, how would you explain this phenomena and its effects?
So this is one of those things where it was a nice demonstration of how many body physics or many electrons interacting with each other gives you something additional and which is surprising to what single particle physics does, single electrons do. So, in 2010, 2011, there were theoretical predictions that when you put graphene on top of graphene rotated at an angle, it was called back then by theorists the magic angle, which is 1.1 degrees, that the velocity of electrons would go to 0. Okay, the velocity of electrons in one layer of graphene is very high. But you put two layers of graphene on top of each other at that 1.1 degree, and their velocity would go to 0. That was a single particle physics prediction, but people did not know what would happen then. Okay, so the velocity of the electrons goes to 0. That means the electrons have very little kinetic energy. People, of course, know that electrons also have potential interaction energy because they repel each other, because they are like charged particles. So, but it wasn't clear at all, because it's very difficult to calculate what happens when electrons interact with each other. What would then the behavior be? And then that meant that for many years, few people paid attention to these papers. They had very few citations, and people didn't even know if these electrons really could go the velocity to 0. And if they did, well, that's a very weird situation. What would happen? But then we made devices. In my group, we fabricated magic angle graphene devices, and we measured superconductivity, which was completely unexpected. No one predicted it. No one thought, and it was a huge surprise for everybody. How come that out of this thing, out of graphene, which is not a superconductor, you put it on top of itself and it becomes a superconductor? And not only that, you could also make it be a correlated insulator. Graphene is always a conductor, but you could make it be a correlated insulator. And nowadays we can make it, we can make it behave like a magnet. We can make it behave like so many things. So that was something which was very surprising, not predicted. And it gives you a little bit of that flavor of how, many body physics, many systems of many interacting electrons can do things which are very counterintuitive, very surprising, and that can be fascinating.
It must also have been unexpected for you to realize this was a worldwide discovery. I mean, when did you and your group realize you've made a breaking discovery?
Well, so the first behavior that we saw was that of correlated insulator behavior, an insulating state where electrons do not conduct electricity because they interact with each other. Even though in principle, single particle physics tells you this should be a metallic state. Okay? The moment we saw that, we realized already this could be quite important, because there are many correlated materials that when they exhibit that type of behavior, they exhibit additional behaviors which are very interesting. So then we started to fantasize that perhaps this could be a superconductor, but it was almost like, well, there's only one in a million chance this will be a superconductor, but let's try. And then the moment we measured the superconductivity, we realized this was the start of a new field, that it was a major breakthrough. It became, very clear to me this was an important discovery, and that this was going to attract a lot of attention, and many groups were going to start working on this.
A lot of people started working there. What keeps you motivated to still work and do research in graphene and being at the top of the field?
Yeah, so that's something very interesting. Of course, if you do something that people find interesting, a lot of people start working on it, and it becomes very, you start to feel that pressure, right? Suddenly, when we started, it was just us. Now there are 100 groups, and they're very good, which means that very quickly I had to accept that most likely the next biggest discovery, it was not going to be my group, it was going to be someone else. There are many very good people working on this, so of course they're going to make the discoveries, and we would be like, I wish I had done that, or we would be scooped, okay? And sometimes, trying to do something and someone else would do it faster than us. But I made my peace with it quite quickly, to be honest, because I thought, okay, we did the founding, we made the founding experiment, and we're still going to contribute, and we have, kept contributing and done many things. And yes, sometimes others will do it. This is good for the field, So it's good when you have a lot of competitors. It means, the problems are interesting. And that brings a lot of people to work on the problem. So it's a community that grows. There is a lot of excitement. My students and postdocs, they go to conference where there are a lot of people working on these things. So it's very nice. It's a very nice feeling having contributed largely to the beginning of this field, which is growing a lot. There's so many fascinating problems to work on, so many things that we still don't understand, that my students and my postdocs and I, we remain heavily motivated. Thankfully, we have been able to continue to be, one of the groups at the frontier. We've done many things that turn out to be interesting discoveries, additional interesting discoveries. So we enjoy it a lot, and that's what keeps us motivated. The fact that you do something that you enjoy and that you're doing well.
Yeah, and that encourages everyone. I mean, feeling the satisfaction of being the father, let's say, of experimentalist graphene. So, and as we approach the end of this wonderful interview, let's encourage young scientists wondering to start. What advice or message would you like them to bear in mind?
The most important thing is do something that you like. Because then if you like something, you don't mind spending a lot of time doing it. You work hard because you like it, so it doesn't feel like work. You're just doing something that it's fun, and then you become very good at it. When you work very hard at something, you become very good at it. And then it's easier to keep being motivated, because eventually, even if there's a lot of struggle, even if it's a difficult problem, when you work very hard at it, if you like it also, things start to work. And then when things start to work, you become even more motivated, etc. A second thing that I would tell young people is take risks. This is more easily said than done. Okay, it's very easy for me as a full professor at MIT to tell people go and risk it, but it's very important to take risks, and when you're young, it's the best time to take risks. Try to be a little bit adventurous. Try to explore things that other people have not done. I always tell my students, we are like explorers in the jungle. We have an idea more or less of where we're going, but we don't have certainty of that anything is going to work. We'll go there with machete, we're exploring, and sometimes we find a nice pyramid, a nice treasure or something. And it's not for everyone. Some people like to know exactly where they're going. They like to know that it's going to work. If they work hard, it's going to work. But if you know exactly where you're going, almost by definition, most of the time is very incremental, the type of work that you do. And that incremental work, it's also very nice and also very important to do it. But to me, it's a little bit less appealing than trying to go and explore. One last piece of advice. Yes. Always try to work with the best that you can afford, the best that will take you as a student. So don't settle for mediocrity or for something that you don't see it clear, but I think it's the only option. Always aspire, try to work with the best. People who are very good. You will learn the most. And of course, they can always say no, but don't be shy. I don't think this group is too famous. Maybe they will not accept me, or they will not take me, or I don't know enough to. If you are eager to learn, there will be someone there that will give you a chance, and try to go with the best.
Okay, this is the end now. Thank you very much for the nice chat.
Thank you for having me.